we will work with the create 3D point cloud by multi RGB images. It means that we will get the real image from the camera, and the camera can move around the plants. How can we do that? Here is the algorithms, the way we do. Look at this is the idea. Firstly, we will get RGB images, and then we will pass it to our semantic topics, semantic models, which we written in Python to create semantic images and publish to our program written in C++ to create a 3D point cloud. This we already done in this date. The ORB-SLAM3 we already built and run in some previous days. Now we use the node RGB-D ORB-SLAM, and we pass the RGB-D images to this node to get the camera pose, the frame pose, and the semantic models will give us the semantic images and help us to create a semantic point cloud. But this point cloud is created by an RGB-D image, just one RGB-D image. Now we want to combine the different point clouds created from different RGB-D images. How can we do that? Because ORB-SLAM3 will give us a pose of each RGB-D images. So we have this pose. We can we can transform the point cloud into the real position of the world, and that can each point cloud each RGB-D image corresponding to each point cloud have their position, have their pose, translation and rotation. So we use this pose to transform them into the real position in the world. That's why each different point cloud will transform with different pose, and this will combine together to make a real scene, to make a real world by the point cloud. However, the ORB-SLAM gives us the pose each RGB-D images, but it has errors. It's called the cumulative errors because we did not perform a loop for ORB-SLAM, so the pose are not like refined or make better. That's why we have to use the ICP method to compare between between point clouds to match, to find another transformation matrix to fix, to refine the combination of the point cloud, and that can help us to have a better 3D point cloud with created from many RGB-D images. That is the idea of our program. In this program, we have to use the ICP method. That's why we have include more libraries here. ICP color. Please download this code if you want to insert in your program. You can download on the program with the final versions. Look at the program. We have include directory. That's why we add the library in wait a minute. We add the library we add the library in the include directories. We project here and include the folder. Okay. Okay, and look at this file. This is really long and complicated, but I will explain a little bit for you to understand. These are the library. There's many library. We want to use the PCL library to minimize the point clouds, to decrease the number, to use the cloud viewer. That's why we have to include this library. Okay. We also include the project.h. This is the library that helps us to perform the ICP method. I upgrade the previous file 3D Sweet Paper CPP, and now we will create with ORB-SLAM. In the previous file, we did not separate or stamp point cloud, the PTO point cloud, or leaf point cloud, but in this example, I will separate them and save in different variable. Say CX, CY, FX, FY is the same as the camera instruction. This is the parameter for ICP method. I cloud RGB is this variable will store the RGB point clouds, semantic point clouds, stamp, the petal, leaf, fruit. We don't use flower and branch, so delete them. This vector will store the point cloud, semantic point cloud, and this will store a list of vector RGB point cloud. Why we have this list here? I will save 3 latest point cloud created from 3 pair of RGB-D images. For us to compare in the ICP method, it would be better if we just compare one by one. It is not good as we compare 1, 2, 3 previous point clouds. That's why I have vectors here to store 3 previous point clouds. This camera pose. Okay, point 1, point 2. It didn't use that. I did not delete them, but I really don't use this. Okay, maybe later. So we talk a little. This is RGB. This is the create new point cloud. This function to help us. Run the ICP algorithm and return for us a transformation between two point clouds. The visualize is the decrease the number of points in the point cloud. There's two types of visualize I use. If we remove the outline point first, it will cost much time. If we remove the outline the points later, it costs less time. That's why with the big point cloud, not really important point cloud, I will use this. With smaller point cloud and with the point cloud we want it like a more accurate, we use this visualize function. Create color point cloud. In this example, I really don't use these functions because I want to save time. Now go here. This is the convex functions that we capture the topics image, RGB, semantic, depth, and position and pose and camera pose. That is to get images. And then this is the function that creates 3D point clouds. As we remember before, every time we want to create a point cloud from an RGB-D images, we call the function create point cloud. But in here we have a different type of point clouds: RGB point cloud, semantic point cloud, stem point cloud, lip point cloud. If we call this many times like this, it has to run the loop many times, so it costs a lot of time here. That's why I have to match them. We have to like using together to run together. Just two loops here, and I will create RGB point cloud, semantic point cloud, and stem and lip point cloud here. With stem and lip, we will select by the colors of the point. After created that, I will minimize the number of points here. If the semantic point cloud is very small, we will return and don't do anything. If the number of semantic point cloud is too high, we must decrease them by increase the resolution, because if the number is too high, is too numerous, the time for running ICP method could be a lot, would be higher. That's make the system run slowly, and we will miss the RGB-D image, so our program cannot run smoothly. If the point clouds are under 400, it lies small, it lies less of 0.7 so I will decrease the resolution to increase the number of points. That could be like more accurate in the ICP method. So this is the algorithm. For the first 2 times we get images, we don't have anything to compare, so we just put in our point cloud. And when the 3rd time we begin to running this function, we have the 4th point cloud. We begin to compare the new point cloud with the previous point cloud. And remember, each time we create point cloud, we have a position, not a position, a pose of the camera, the pose of the frame. Therefore, when we create 3D point cloud, we have the points word here. We have to transform the point into the word position. That's why we have this command that helps us to transform the point cloud into the word position. But after that, we have to run the ICP method to make it better. This is the function that helps us to run ICP method. Since the 4th frame, we will compare the previous point cloud. It is the source cloud and new the target point cloud is our our new point cloud. If the semantic is so small, we use RGB to compare. If the semantic point cloud have more than 400 points, we will use the semantic point cloud to compare. And after we run this ICP method, we have a transformation, and with the transformation we will have to transform all the point cloud, the SLAM, RGB and others, to make our semantic point cloud is better. Okay. And then this is where I will it is like a stack. We push new point cloud in the stack, and we pop the oldest point cloud. And every time we find a new point cloud, we add to the old each step we add a new point cloud to our point cloud, to the final point cloud. And the viewer will show the final point cloud created by 3 point cloud in the stem, leaf and petiole. Okay. This is we want to decrease the number of the semantic point cloud, because we use that to compare in the ICP method, so that's why we have to decrease them continuously to make it smaller. That is how we did. And remember, in this function we not surprise only semantic and depth. We surprise the 4 topic: RGB, depth, semantic and the camera pose. Okay, and remember we changed the message fielder into for, and we pass here 4 parameters. That's all. There's a difference a little in the Python note. Previously we read directly from the camera, so we have here camera color image raw, camera align depth to color image raw, but now we will read from the ORB-SLAM3. ORB-SLAM3 draws RGB depth and cameras. And we publish RGB semantic depth mask post, but we don't need mask, so we didn't read mask. Okay, and then because we have to run many different nodes, so I create here a launch file. In this launch file we will start 3 nodes. The first node is ORB-SLAM3 RGB-D images. This will read the image raw from the camera, and then I will start the street paper ORB-SLAM3 Python node, and finally I will start our 3 street paper ORB-SLAM create point cloud. So we use this launch file. It's easier than we have to open 3 different terminals and type the command to start 3 nodes. It takes a lot of times. Okay, after you create this, I already built by run catkin make here. But if you not, please run catkin make, because before you use that. So I will start the launch file by roast launch. Where is that? It's roast launch read image back sweet pepper launch OS here, but I don't know why it did not display it. I enter that, it worked. Okay, so we have a voice cloud, a map of ORB-SLAM and RGB viewer ORB-SLAM, and I will start the backfire. We will run the lab 8. Okay, and let's see. You see that the camera is go up, and when the camera moving up, we will get the new RGB image and new post, and we will calculate the transform matrix in the ICP method to refine the transform positions to make it better. And this is the RGB and semantic image is time we create, and the cameras are moving down. This is the voice cloud. That's all. After it's finished, that's all for create the 3D point cloud. Next, we will learn how to find the cutting point.